Topic 7.1 Summary, Part 5, The Law of Radioactive Decay. We're going to talk about half-life. When the atoms in a substance are giving off alpha or beta particles, or gamma rays, we say that the material is radioactive. The process of giving off a alpha or beta or gamma ray is called radioactive decay. Radioactive decay is random. What that means is for a given nucleus, we can't predict when it's going to give off a particle, when it's going to decay. Radioactive decay is spontaneous. What that means is it happens all by itself. It can't be prompted. And it's proportional to the number of undecayed nuclei. And the number of remaining parent nuclei decreases exponentially. If you look at the equation at the bottom of the slide here, what that's saying is that the rate of decay, delta N, is the number of nuclei which are decaying, changing to something else, giving off a particle. The change in that per unit time is proportional to how many atoms of the undecayed parent and nuclei there are. For a given nuclide, we can measure something called the half-life. The half-life is the amount of time during which 1/2 of the parent nuclei will undergo spontaneous decay. Half-life is also the time that it takes for the activity to drop to 1/2 of its previous value. And the half-life is not affected by any physical conditions such as temperature or pressure. In fact, there's nothing we can do to change the half-life. It's a natural constant. It's sort of like a built-in natural clock. Here's a typical decay curve. If you look at the y-axis here, it starts at 1, so there's 100% of the atoms are of the parent nucleus. After a given amount of time that we'll call a half-life, half of the parent nuclei have decayed, which leaves half of them undecayed. During the next half-life, the half that have not decayed, half of those will decay, leaving 1/4 of the original parent nuclei. During the next half-life, 1/2 of that quarter that's remaining will decay, leaving us with 1/8, and so on. As each half-life goes by, the number of remaining parent nuclei becomes 50% of its previous value. Here we have another graph depicting half-life. At the top here we have N0, which represents the sample of material where all of the atoms are of the parent nucleus. And after one half-life, half of those atoms have decayed, leaving us with 1/2 that have not yet. And during the next half-life, half of that 1/2 will decay, leaving us with 1/4 of the original sample. And during the next half-life, 1/2 of that remaining 1/4 will decay, leaving us with 1/8 of the original atoms being parent nuclei still, and so on. The half-life of a nuclide varies dramatically. So here's a chart with just a few samples, kind of the extremes. So at the top you see we have polonium-215, which has a half-life of 18/10,000ths of a second. So it wouldn't take very long before all of the sample of polonium-215 has converted to the daughter product. But somewhere in the middle here we have iodine-131, and it has a half-life of 8 days. Iodine-131 is used in medical treatments. And at the very bottom, we have uranium-238, which has a half-life of 4.5 billion years. That's about the age of the Earth. Here's a table just showing the fraction and the percentage of the parent nuclides left after a certain number of half-lives. So at 0 half-lives, we have 100% remaining. After 1 half-life, we have 50%. After 2 half-lives, we have 25%, and so on. And after 8 half-lives, we're down to 0.39%, almost nothing. That's it. We'll see you next time. Except I do have a wacky word of the day for you. Today's definition is eyedropper. Eyedropper, a clumsy ophthalmologist.